Hi again. So last time we looked at some of the theoretical considerations and a little bit about how we could use the finite difference method to simulate the wave equation for that simple kind of shallow water effect. The implementation that we saw last time was in JavaScript, and we're actually going to look at the source code of that, which is all contained in this one JavaScript file here. This is literally the presentation we saw last time, and all of the simulation bit actually gets invoked in just these couple lines, and there's a thing to re-trigger the simulation to start over when we go back to that slide every time. But so basically everything is in this one JavaScript file, wave simulation.js. Again, this is on GitHub. Um, all this is going on in just like 120 lines of code, and like you can tell like half of it is comments, so there's not really a whole lot of logic to it. Um, so let's start from the top. In order to abstract the concept of grid and the values on the grid, so those were the function u in our original video, in the first video. So remember at each location kind of in this 2D pool that we were looking overhead, um, there was a value that was explaining the sort of height relative to some equilibrium in the pool. So um, in our case, we're going to look at an n by n grid, a square grid, like what we were looking at before, and just a couple little helper methods to help us look at reading and writing to that grid. This is probably super trivial for everyone, but I'll just go over it really quick. So you can invoke one of the, or you can construct one of these grids of size n. It's got some simple storage, just looking at, pushes on n squared of those values. And then whenever you need to actually go read a particular value from that grid, you're going to reference, cell I and j both are in the range 0 to n inclusive. And so it actually return the value that's at that grid point. Okay, just some simple indexing. And then to actually write a value, it's the very same thing, you're just writing something. So that's all there is to the grid object. Very, very simple. So the wave simulation is a couple pieces. So it's actually stores a couple of grids inside of itself, and a couple of parameters that we need in order to simulate things. We'll go about that in just a moment, but I just want to get a high-level overview. So there's a step function which actually steps forward our simulation by a small amount of time, dt. And this is what's actually causing the thing to sort of change over time. So every invocation of this causes the simulation to get updated to the next frame. The thing that's actually drawing it to a canvas, though, is this write to canvas function. We'll go over this again. This is sort of a convenience for the presentation. You don't actually really need this, but ClearGrid is just literally setting both of the grids that are stored inside the simulation to all zeros in every cell. So you probably don't even need that. I just used it for this presentation. And again, start is another function that just is kind of used again for the presentation. So let's just go back to the constructor for the wave simulation. So internally, the simulation needs to know what its resolution is. You can optionally pass one here. Otherwise, it defaults to 64. So we had a constant that appeared in our last video that was multiplying the Laplacian. So that thing, I told you it was the wave speed. It was the c in the original equation. So basically it was the c times dt squared over h squared. It was explaining how quickly our waves move. So sigma here is going to be all of that stuff multiplied and divided together. It turns out that actually this can not actually be that high a value. So I'm going to go ahead and fix that. I'll have to explain that in a future video. You can't actually make the waves arbitrarily fast because of something called the current Frederick-Levy condition. You may see it written as CFL. There are sort of some limitations on the idea of finite differences and finite element methods and other integration schemes. So basically there's some theoretical underpinnings that says you can't really have like ridiculously fast traveling waves and stuff without some what's called numerical blowup. Whatever. We'll talk about it in a future video. For now, it's just, this number sigma needs to be between 0 and 0.5. I can't have waves going any faster than that without having the thing break. So you'll notice in the last video, we said that we were going to be computing the new frame, the next frame, using our current frames data and also the last one. So it's not enough for us to just kind of know what our current state is. We also need to kind of record what the last one is. So we need to actually store two grids, the current one and the last one. And there will be a kind of little leapfrogging method for actually overriding the older grid with the newest grid. I'll illustrate that in a little while. And then there's a kind of just a pointer to which one is actually the older one right now. So basically the entire video that we just went through is how to actually evolve this thing over time. So that's what this step function is doing. The only user-specified value is how what the step size was, dt. Right. So we first make some references to what the most recent grid is. So that's actually going to be kind of what's being displayed in the current frame. So this is going to be a grid object that we saw constructed above. So there's only two grids, so we're 1 minus current grid. And then the older of the two grids that we have on hand is going to be the other one, so not 1 minus. Alpha is going to be the dt squared, so the user passed in dt, and then sigma is basically accounting for the c over h squared part. So alpha is that one constant that is in the end going to end up specifying how fast the waves move. So with our selection here, 0.5, and like I told you, sigma can never be any greater than 0.5. dt can never be greater than 1 in this case. So that the final coefficient there is never greater than 0.5. Okay, and then we need to actually execute the update logic that we explained in the last video. So we need to update every single one of the cells that's in the grid. You'll notice that this doesn't go from I equals 0 and j equals 0 to I less than n. We're actually only going over the interior ones. So the ones on the very edge, the boundary of the domain, like we were saying, we're going to leave those boundary ones as they are for all the time. And we'll only update the inner ones. That sort of makes some sense if you think about it. Simply, remember each grid cell actually needs to read information to its left, right, top, bottom. And in order to keep things simple, we're not going to like loop the grid over from the top to the bottom and to the left or the right. You could actually do that to simulate waves traveling on a torus. Maybe we talk about that later, but just to keep things simple, we'll just update the internal cells of the grid, so everything but the boundary cells. So we had that expression that was for the Laplacian at a current grid point. So all of this is happening at a particular grid point now, ij. And we want to compute the Laplacian. I told you that was just the sum of all the neighboring cells. So I plus 1, I minus 1, j plus 1, j minus 1. And then you have to subtract 4 times the actual cell that you're trying to calculate the Laplacian for. So that will give us the Laplacian value. And you remember that the original that approximation for the second derivative on a grid actually requires you to divide by h squared. Well, we're just going to assume that h is 1. So that makes a lot of this stuff just a little bit simpler. And then in order to actually compute what the new value should be, so this is the value that actually is the next frame at location ij in the grid. We had that other update equation that was doing integration in time. So 2 times the current frame that we have right now minus the value at the older frame plus alpha, which is explaining the wave speed, and then the Laplacian value that we just computed, which is again explaining kind of the bumpiness or the curvature in the grid that we can see. So if you do this, this calculates a new value, which I have wonderfully titled new value, which is the value that we're going to set this grid cell to for the next frame. So we're doing this for every cell, and you can tell we're updating older grid. So we'll explain this again in a minute. I'm going to have a diagram, but basically, if you look at this, the older grid value is never used anymore. It's not like neighboring cells need to look at it or anything. So it's the older grid value is actually used precisely once in this update, and so we can actually overwrite it. And what that does is actually mean for the next frame, if we go sort of into the future, older grid is then going to be what our current frame is, and what we were calling recent grid will now be the oldest grid. So we'll show that again in a minute, but basically we can overwrite the older grid with this new value. And so at the end of this, all of the interior cells will have been updated with that dynamics, the procedure that we came up with last video. And just so that we're kind of ping-ponging between these two grids correctly, I'm going to flip that pointer so it's pointing at the other one. So I just wanted to briefly explain what I was talking about with the kind of ping-ponging between different grids. So you notice that we had two different grids. I'm just going to call them A and B. We called them recent and new, I think, in the code. Oh, that's not a B. So this was kind of the current frame that we were drawing right now, and this is what we were calling sort of the older frame. So A would be, if we imagine now, B is what we're showing, and A is what we were showing kind of the last frame. So we needed somewhere to put this next frame of data that we want to show, and that we'll need for subsequent frames, of course. So the sort of trick here is that you can get away with just using two and not needing a third grid to write the new result into, because you really kind of read the value at cell ij from the older grid A here. You only read it once, and then it's never needed again. Like, none of the other grid cells need to reference that anymore or anything. So what we can actually do is use the value at cell ij and B and the cell at ij and A, and actually overwrite A. So we'll kind of we'll use both the grid cell values from B and from A, and then actually overwrite the older grid with the newest value. We couldn't write into B, so like maybe you're asking why can't we just write into B? So actually the other grid cells do need to know their neighboring grid cells values in the current time step. They don't need to know it in the older one, but in the new one they do. So that's why we can't write into B again. If that were possible, we could just we could be able to get away with one grid. So yeah, so the same thing will just keep happening in the next frame. We'll in this one, in this case, our older grid was A and our newer grid was B, and then we were able to overwrite in A. Kind of in the next frame, B is going to be our older, and A is going to be what we're currently showing. And you guessed it, we're going to overwrite into B in the next frame. And then this process just repeats, so we end up ping-ponging between the one we're going to write, A, B, A, B. It's just a good way to save a little bit of space. You just have to keep track of which one's older and which one's the more recent one. So that's why we have that extra pointer in the code. Okay, so to actually get some sort of visualization as to what this looks like, the one that we saw in the presentation, I'm just kind of writing this to image data on a canvas element. And literally all we're doing is just walking through the pixels of that image data. We're going to read the value in the grid. So in this case, the canvas is the same size as the simulation pretty much. So what we do is read the value that's in the grid. And then those values can be, so this is depending on how you actually set up your grid and what you kind of poke it with. So what you set some of the values in the grid to, kind of what range those values can be. But in general, mine were, I was kind of planning that they would be on the range from -1 to 1. So in order to put them on the range of 0 to 1, I add 1 and then divide by 2. Just to get a little bit of a different kind of palette, I'm just squaring this, so this is going to make all of the colors a bit darker. We have to move it into the range of 0 to 255 and make it integer. And then I'm also clamping, so if any of them are negative or greater than 255, just clamping to that range. So everything at the end of this is between 0 and 255 inclusive. We then have to write, this is all very boilerplate. So it's just computing an index into the canvas image data and setting the red, green, and blue to that same thing. So we're going to go to grayscale color. And then the alphas, obviously, we want that full. So this part is, not really got much to do with simulation. I just wanted to explain very briefly, what that was doing. Yeah, so that's pretty much it. So if you have any more questions about how this code actually works, or you think I could provide provide some more details, please leave a comment. Thanks.